Hi there. In this video, we're going to continue looking at equality testing in floats and some of the issues that arise because of the fact that floats cannot be stored exactly, at least the binary representation of a float isn't necessarily a finite representation, which means we only have an approximation to the number that we want to store. So, for example, we saw that if we take x equals 0.1, then if we format x to actually display, let's say, 25 digits after the decimal point, we end up with this number here, right? So 0.1, even though if we print x, it will tell us 0.1, in fact, it's not exactly 0.1. On the other hand, we might have something like x equals 0.125. Now we know that that is equal to 1/8. So that is a power of 2 in the denominator. So we do have an exact representation for that. So if we were to take this code again, then as you can see, we do have 0.125 and then everything is 0 after that. So that works, right? Which means that if we do something like this, x equals 0.125 plus 0.125 plus 0.125, okay? So that's x. And let's say we set y equal to the sum of those three numbers, which is 0.375, okay? Then if we say x equals y, that will return true. Well, that's because those two numbers, 1/8 plus 1/8 plus 1/8, those were exact representations. So the sum becomes an exact or a finite representation. And then y is the same thing. It has a finite representation, and the number of significant digits fits within what can be handled by the float type in Python. So that works. But on the other hand, if we do this, let's look at 0.1 as we did before. And let's say y equals 0.3. Then when we do x equals y, that turns out to be false. And that's because 0.1 and 0.3 do not have finite binary representations. Therefore, they can only be stored as approximations in our float data type. Okay. So how do we compare floats? And we looked at that in some detail in the previous video. And we really have two ways of doing it. One is to round. We could do something like this. We could say round x, comma 3 equals round y, comma 3. So we're rounding x and y to 3 decimal points. Now, what are x and y? Let's just print that out quickly. Let's let's format x25f. Helps if I type it correctly. Okay, so that's x, and y, we can do the same thing to that, and we get that. So as we can see, these two numbers are not exactly the same, and so when we round them to 3 decimal points, what's going to happen? We get true, right? And that's because it's rounding this 29999 to 0.300, which will be the same as this round here. The problem with round is that if you think about what round is doing, it's basically doing a test to see how close the two numbers are within an absolute tolerance, right? Because we're rounding to 3 digits after the decimal point. We're saying, are they within, that number here? Are they within 0.001 of each other, essentially, or 0.0001, right? 3 zeros and a 1. And of course, that has problems. And we saw that when we looked at the isClose method. We looked at using absolute and relative tolerances, and we saw that absolute tolerances can be a problem when we're dealing with large numbers compared to numbers close to 0. So what do I mean by that? Well, if you take a look at two numbers, let's say x equals 10,000.01, and let's say y equals 10,000.02. Now, because of the magnitude of the two numbers, we might really want to consider these two numbers to be equal. But what's the delta? Well, the delta here is equal to 0.1, right? I'm not going to write that, but that's the delta. And so the delta is 0.1, and we would probably want to consider these two numbers as close to each other. On the other hand, if we take 0.01 and y equals 0.01, well, 0.02, what's the delta here? It is also 0.01. And yet, relatively speaking, x and y are very different from each other. Why? Well, y is 2 times x, right? Y is not 2 times x here. It's a very small difference, right? In fact, if we want to see what that is here, we can just say y divided by x. That will give us an approximate value. It's 1.000999 times x. Whereas here, if we do that, y divided by x, we get that it's 2 times. So that's kind of an issue, right? Because do we consider this close? Do we consider that close? It kind of depends on the problems you're working with, in part. But generally speaking, using this absolute tolerance is going to cause a problem, right? Because it might work and say, yeah, you know, if I round these two numbers, they're not close. Now, if I round them to, let's say, 1 decimal point, then they're not close. And if I also keep round 1, so round to 1 digit after the decimal point of these two numbers, they will also be considered not close. Let's take a look at an example. Round x comma 1. Okay, what does that give us? That gives us 0.0. So if we do that and y comma 1, well, we get that they're true, right? They're close to each other. And in fact, we probably would say, no, they're not close to each other, relatively speaking. On the other hand, if we take x and y equal to those two values, and then we round them off and check up what happens, it tells us that it's true. And in that case, yeah, they're close enough, because relatively speaking, they're close to each other. So for that reason, we're going to use the is-close method instead of the round method, since the round method really is only an absolute tolerance kind of technique. So for that, we're going to import, so from math, we're going to import the is-close method. And if you want, you can always get help on the method itself in your Python console this way. And we can see, as we saw, that is-close takes two parameters, the two values a and b that we want to check if they're close to each other, and then the relative and absolute tolerances, which are optional parameters. And if you don't specify relative tolerance, it will default to this value here, 10 to the negative 9. And if you don't specify the absolute tolerance, it will default to 0. Which means in essence that if you don't specify the absolute tolerance, we're ending up with a method that only uses the relative tolerance. And as we saw before, using only a relative tolerance can also cause problems. The best way to deal with something that kind of fits just about any number you'll encounter as your program is running is to use both relative and absolute tolerances. So let's take a look at some examples of that. So let's say again, let's go back to our standard one, okay? So we'll look at that. And we're going to use the method as is. We're not going to specify the relative and absolute tolerances. And we're going to ask whether they're close. And the answer is true, okay? So whereas if we had done x equals y, obviously we get false, all right? So that's kind of a very simplistic way of using the is-close method. You just use the defaults. It uses a relative tolerance, and it kind of works. But let's take a look at numbers like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9.01. And let's take it y equal 1, 2, 3, 4, 5, 6, 7, 8, 9.02, just to change up numbers a little bit. Okay? So in this situation, we might consider x and y to be close to each other. Why? Because relatively speaking, they are, right? But if we take x equal to 0.01, and if we take y equal to 0.02, well, we don't consider those close to each other. So let's go ahead and look at what happens if we use the is-close method with those two numbers, x and y. And here, I'm going to specify a lower relative tolerance. So we'll specify this, and what do we get? We get that it's true. And here, if we use is-close, x comma y, and we'll use the same relative tolerance. That's the important part here, is that we don't have to change our relative tolerance. And then we get false, which is kind of what we would expect, right? I mean, again, depending on the problems you're working with. But 0.01, 0.02, relatively speaking, are very different. Whereas, relatively speaking, these two numbers are quite close to each other. But we have to be careful when we deal with relative tolerances only, because right now, remember, the absolute tolerance is what? It's 0, right? It's not being used at all. So we have to be careful with small numbers. So let's take x equals 0 point, and let's put in 6 zeros, 1, 2, 3, 4, 5, 6, 1, and let's take y equals 0 point, 1, 2, 3, 4, 5, 6, 2. And let's look again at the isClose method with x and y, and again, we'll keep the relative tolerance to 0.01. And we get false, right? So now we might be getting to a point where we're dealing with numbers where, you know, maybe we're only dealing in digits or numbers that should be accurate up to 2 decimal points. And so that's why we put our relative tolerance to that, let's say. But in this case, this is still not close. So that's the problem. When you're very close to 0, the relative tolerance is really going to cause you a problem. So we would want to use an absolute tolerance in this case, right? We would check and see, is the delta, you know, x minus y absolute value, is that less than or equal to, let's say, 0.01? In which case, yeah, we'll say they're equal, right? It kind of depends on how many significant digits you want to work with. Okay, so what we can do here to fix this is to use the isClose method. Again, why? We'll leave our relative tolerance equal to 0.01, but now we're going to specify an absolute tolerance as well. And let's say that we want the absolute tolerance to be also within 0.01 of each other. And so now we get that it's true. Okay? So that's why we want to combine relative and absolute tolerances, is because we can set those tolerances up, you know, once and for all in our program. It's rare that you would change your tolerance levels as your program is running, because you don't know what numbers you're expecting, you know, necessarily. You might know the ranges that you're expecting, and therefore you can set up ahead of time and determine what your relative and absolute tolerances should be when you're comparing floats. But in general, you're not changing your tolerances as your program is running, because you don't know what numbers are coming at you. So you set them up, and you set both the relative and the absolute up, and that way it can handle most cases. So let's take a look at another example. So again, 1, 2, 3, 4, 5, 6, 1, y equals 1, 2, 3, 4, 5, 6, 2. And let's take a equal to now that big number we had before. Okay, and b equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 2. Okay, and now we're going to print is close x comma y. So we'll take the first two numbers, we'll set up an absolute tolerance of 0.00, let's say 0.1. Let's say we want to go there for the absolute tolerance. So if numbers absolutely are within 0.0001 of each other, they're considered close, right? But of course, we also specify the relative tolerance so that as the numbers get larger, then the absolute tolerance maybe doesn't matter as much. And we want to see if, relatively speaking, they're close to each other. For small numbers, we look at absolute tolerances. Large numbers, we'll look at relative tolerances. So let's do that. And let's also do the same thing, right? Now, in both of these cases, we would consider these two numbers to be, let's say, close to each other. Because, you know, they're quite close. They're within that tolerance, absolutely given, absolutely speaking. And these two, well, they're definitely not within 0.0001 of each other, but relatively speaking, those two numbers are pretty close to each other. So I know I'm rehashing this stuff a lot, but it takes some getting used to. And then we'll just specify the same, and that's the important part here, is that we can specify the same absolute and relative tolerances. We don't have to change them according to the numbers that we're examining. And as you can see, we get that both are true. Okay, so this kind of wraps up how we look at equality testing for floats. And so we have to be a little careful. It's not as simple as using an equals equals, and even rounding, although it can work in some cases, doesn't work properly when we're talking about relative and absolute tolerances, since rounding basically only does an absolute tolerance check. All right, thanks for watching, and I'll see you in the next video.